All right, so now we're going to do our next thing, which is looking at the impulse input, which is going to result in an impulse response, which, as we move into one of our future topics, we're going to need, and we'll explain why. But for now, we need to deal with what in the world is an impulse response, what is an impulse, and then we'll get into getting an impulse response. So a unit impulse is it's a theoretical concept, all right? Nobody can really quite have it for what it is. We can calibrate impulses in the real world and calibrate the responses for what we need them to be. And these are used, okay? Uh, but mathematically, what is it? We'll get into the logistics a little later, talk about that. So an impulse input, you have to somehow put a metric to that. So what is a unit impulse? Well, in terms of if you were to plot it, it would look something like this. It's at zero, and at the time it happens, okay, so an impulse happens when this argument in here, t minus t0 equals zero, boom, that's when it's happening. Okay, so at t0 it happens, and so it just ahead of t0 in some sense, it just goes way up and then comes right back down. All right, and this spread here is negligible. And okay, it's epsilon dt. It's just extremely small. So that's kind of makes sense. Something comes up and I was like, boom. All right. Mathematically, what is it? Well, this is where it gets kind of interesting. A unit impulse, if you were to measure from minus infinity to positive infinity, so it's always zero, wham, then always zero again, the integral under the curve is 1. So that's what a unit impulse is. Somehow, the area under here is 1, and it is equal to 0 everywhere but where it happens. So now you see it's a very theoretical concept, okay? Because that don't work. But it doesn't work in reality, but mathematically we can play with it. So you might say, well, what is that? What can we model this as? Well, this. Picture at t0, we have a step up, and at t0 plus 1 over n, we have a step down. So if you look at that, this would have, and in each case, whatever n is, this thing is height n. So here we have 1 over n in spacing, here we have height n. Well, if you take a look at that, that's n by 1 over n, the area is 1. Okay, and you take the limit as n goes to infinity, you get that. Okay, so we're now starting to be able to kind of define this mathematically, but it has one more really cool property, which is known as the sifting property. What does that mean? Okay, if we were to, here's an impulse that happens at time t0. It has all these properties. Well, this is just a way of modeling it. But it has the area under the curve of this is 1, and everywhere but at where if you're not at the point that it happens, it's 0. Here's the property. So it has area 1. If you have ft times this thing of area 1 that happens over this very, 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 very small amount of time, you get f of t0. So this force scales the impulse. So you get whatever this function is at time t0. That is called the sifting property. So why do they say that? Because you have this function here, and it sifts out the value of the function at the time of the impulse. That is the sifting property. So we're going to play with finding the solutions to differential equations where we apply a impulse that has the following properties. The area under the curve is somehow 1. It's everywhere but where it happens, it's 0. And it sifts out the properties of anything it's multiplied against, or the value of whatever it's multiplied against. All right, so let's go back to the same differential equation we've been using and using and using and using. All right, so 2y dot plus 10y equals 3 times an impulse. All right. Now notice I just have a t by itself in here, so that says this impulse happens at time equal to 0. this argument equals 0 when t equals 0. The initial condition I wrote as y of 0 minus. Why did I do that? Okay, what the impulse does is it shifts the initial condition. So the system is at this point. So just picture you're standing there and somebody suddenly goes and punches you in the jaw. You had some position before you got punched. And then in response to getting hit, you move, okay, to another position, and then afterwards you start yelling ow when other things happen. All right, so that's very important. This is at y is 0 minus. This is the position of the system just before the impulse happens. All right, so let's move on for this. So here I explain this. T is 0 minus, time just before the impulse hits. So the impulse is considered to hit between 0 minus and some 0 plus. And then there is no inputs. After 0 plus happens, when the impulse is gone, there's nothing left. So how are we going to solve this problem? Well, we need a little insight from baseball, let's just say. So let's take a little insight from baseball. What can we say? If you go to hit the ball, you have your bat, pitch comes in, you go to hit the ball, the bat provides an impact, okay, like an impulse. Okay, so the ball's coming in and an impulse is applied to the ball. Let's think of what happens. This is important, okay? If you're watching the ball, if you ever see something in slow motion as a 90-mile-an-hour fastball comes in and the bat hits the ball changes in velocity and acceleration basically instantaneously. Boom, it's going the other way, faster than it came in. All right, so velocity and acceleration change in an instant. However, if you look at the position of the ball in the bat, it spends virtually no time in the bat, and the ball, while it's in contact with the bat, barely moves. Okay, so we have the position almost doesn't change during impact. Okay, and an impact is really, really small amount of time. So what does that mean? Okay, if you were to take this ball that's thrown at 90 miles an hour and the bat hits it, if you look at the time of impact, that'll be from like a 0 minus to 0 plus. We have some change in position horizontally, and it may get loft too. I'm not going to worry about that. But the change in position during the impulse is extremely small. And if we integrate this, okay, the time that the ball is getting hit, even smaller yet. So we have extremely small, just a couple of centimeters, times virtually nothing. If you integrate all of that, what do you get? Basically 0. For a perfect impulse, it would be 0. So this is the insight. If we integrate position, we get 0. That's what you got to come away with here. That's the important point. So how do we handle impact? Well, if you recall dynamics, you use momentum. All right, so that's how we did it. So that's what we do here. So you have some amount of momentum coming in, picture baseball. An impulse is applied by the bat, and that gives you the new momentum as it comes off the bat. That's simple. Okay, and just so to recall, this is the equation you had. Here was the impulse. The integral of the force, dt, from the time of this impulse happened, here was the final momentum, and then you just brought the momentum to the other side, minus the first momentum. Okay, so you all had that. All right, so here's our problem. Here's the differential equation, 2y dot plus 10y equals 3 times an impulse. I'm going to integrate that over the impulse. So if I do that over here, 3, the integral of the impulse is 1, but I multiplied it by 3, so constants go through. So this integral is a 3. All right, now we're going to take a look at this side. All right, if I integrate 2y dot, okay, I get 2y, 0 plus, 0 minus. plus 10 if I integrate y dt. We just had a discussion over this. This is 0. This term goes bye-bye. So now I have, okay, 2y of 0 plus. So this is where is the position right after the impulse. Here is the position 2 minus 2y0 minus, the position just before it got hit upside the head, equals, all right, so I just restate that, 2y0 plus minus 8 equals the other side, 3. Bring the 8 to the other side. So now I have 2y0 plus equals 11, divide by the 2, and we get, that's kind of ugly, y0 plus. 11 over 2, 5.5. All right, so now, here it is right after this has happened. So let's look at, we can write the response right now. So it's starting at 4. It's sitting at 4, okay? And then, boom, it gets hit. Time equals 0. And it jumps up to 4.5, basically instantly. That's how we model that. And now the impulse is done. We simply have an initial condition response. And it just dies out. And we can just write that. We don't need to solve it because here was the same differential equation. The root is at minus 5. So that's just going to be e to the minus 5t, 5.5 e to the minus 5t. And at 4/5, because that's our settling time, it's gone. So here's our response. And that's how you handle impulses with first order systems. It's basically the same with second order. Couple little nuances. We'll talk about that later. That's all for now. Take care.